I'm going to solve some simple basic problems on waves, traveling waves. So here's the first example to get started, a really simple one. So the displacement of a wave traveling along x-axis is given by this equation. So you're given the wave function for the given wave, where x is in meters and t is in seconds, and these are the questions. So it's asking what's the frequency, wavelength, the speed of wave and its direction, and calculate the transverse speed of the particle of the medium at t half a second and half a meter. So let's get started with the equation. So to find the frequency, wavelength, first you have to compare the given wave function with the standard wave equation, right? So let's first compare. So 5.2, and it says this amplitude is in centimeter, cos 5.5. So this is in radians per meter, right? And I'm just gonna write down the numbers. Plus 72, this is in radians per second, times t, plus pi y over 2 angle, phase angle, and compare. So you always want to compare with the standard wave equation, and our standard wave equation for a traveling wave, the wave that travels, right, is amplitude cos kx plus omega t plus some initial phase angle. That's our standard wave equation. So just need to compare. So where okay, so first question is what's the frequency? So to find the frequency, you have to compare with this. So omega has to be from this, it has to be 72 radians per second. This is already in radians per second. So then you can find, so omega is 2 pi f is 72, so frequency is 72 divided by 2 pi, and if you do that, it's 11.5 hertz. So that's the frequency of the given wave. Second, what's the wavelength? So to find the wavelength, you have to compare this k. This 5.5 must be k. So what is k? K is a wave number. It's called wave number. So go back to my lecture slide and see the terms. So k 2 pi has to be 5.5. So that's why lambda, which is the wavelength of the given wave, has to be 2 pi over 5.5, and that is 1.14 meters. Okay. So that's the wavelength of the wave. And next, what's the speed of the wave and its direction? So that's really easy now. The speed of wave is just lambda times frequency product. So lambda is 1.14, frequency is 11.5, so it's about 13. Okay, 13.1 meters per second. That's really easy. So next is calculate the transverse speed. Okay, so don't get confused. So don't get confused. So if you draw the wave pattern, right, y versus x, right, y versus, so we're gonna check, it's asking what's the transverse speed of the particles of the medium at t half a second and at what distance, at a half a meter. So I'm just gonna so I'm sorry, this is y versus x, right? So this is the wave pattern at some particular time, right? But we're gonna see the particles just oscillate simple harmonically. So we're gonna just see at half a meter distance, how particles are doing. Right? So you are just plotting y versus t now, right? Because you're just, the particles are just simple harmonically vibrating. So it's a y versus time at half a meter. Let's say half a meter is right here. This is, so at a half a meter, right? If this is a transverse wave, the particles are just doing like this, up and down, right? If this is a longitudinal wave, it doesn't say it's a transverse or longitudinal, wave equation would be same. If this is a transverse wave, the particles would be just oscillating up and down like that at half a meter. And if it is a longitudinal wave, the particles would be just oscillating like that. So we're gonna find at the second graph is at 0.5 meter, the particles would be just simply oscillating back and forth, and its wave equation is just this, right? So then we will just begin with so to find the transverse speed, So let me first write down the given wave equation. So the wave equation is of this type: cos kx plus omega t plus pi over 2, right? And so first of all, v is the transverse. To find the transverse speed, you have to take the time derivative of that. So it's cos of derivative of cos is negative a, and then since you are taking derivative with respect to time, so you have the coefficient omega and sine kx plus omega t plus pi over 2, and just put all the numbers from the given question, right? You have v is a is 5.2 centimeter, but I want to calculate everything into standard unit meters. Omega is 72, and sine k is 5.5, and x is, we are finding the transfer speed at half a meter. X is, that's given, plus omega is 72, and you are finding the speed at half a second, so t is also half a second, plus pi over 2. And now just do the calculation, but remember, make sure, it's important that your calculator must be in radian mode. Make sure to, just for this calculation, the calculator must be in radian. Why? Because all of these are in radians. This is in radians per second, this is in radians. Just put the calculator. So if you do that, you're gonna get negative 1.86 meters. So that particle in the medium has a velocity of negative 1.8286 meters per second at half a meter distance at half a second. And this transverse speed could be completely different from this wave speed, right? Completely different from wave. The wave speed was 13.1 meters per second, way different. Okay, these are two different things. And also the wave as a whole is traveling in, the wave is traveling in negative x direction, not positive x direction, negative x direction. Remember, in our lecture we talk about that. If you have a positive thing here, the wave is traveling in negative direction. If you have a negative here, the wave is traveling in positive x direction. Okay, so that's how you calculate. So here's the next question. So this is the snapshot of the wave, at t is equal to 0 seconds. Okay, you take the snapshot of the moving wave at t 0 second, and this is the y versus x graph at t 0 second, and it's asking what's the amplitude, wavelength, and the frequency of the wave, and write down the wave equation, and what is the maximum transverse speed of the particle. Okay, so first question is so let's figure out amplitude, wavelength, and frequency. So amplitude is again just the maximum displacement, right? So that's 4 centimeters, right? If you want to do it meters. So and what's the wavelength? So wavelength is, so this is y versus distance x, right? So if you are given the wave function, wave pattern in y versus distance x, all right, so peak to peak distance is your wavelength. This is your wavelength. Okay, so this is 2, this is 14 minus, so lambda is 14 meters minus 2 meters, so 12 meters. What's the frequency? So you are given the wave, this is the wave speed, the speed of wave. Okay, you are given the speed of wave, right? So then since you already know the lambda, then you can find the frequency, because v, speed of wave, is lambda times frequency. So frequency is v over lambda, so v is 24 meters per second given, and lambda is 12, so just 2 hours. Okay, so that's the part A, really easy. Part B, write down the wave equation for the given wave, right? So let's first figure out what you need to write down the given wave equation. So the wave equation, which is function of both space and time, is a cos kx plus and minus, right, omega t plus some initial phase. So we're going to need k. What is k? K is 2 pi over lambda, which we already know. Right, so 2 pi, lambda is 12, right? So that's going to get you 0.52 if you do, and omega is 2 pi f, so 2 pi, and frequency is 2 hertz, so that's going to get you you know, about 13 radians per second. And what else do you need? So you still need this phi, the initial phase, right? So how do you find the initial phase? To find the initial phase, this is already at this wave is already frozen at t0 seconds. So you just need to find out what's this at x is equal to 0 to find. So here from the given equation, so you already know all these, right? So y is the displacement at x0 is 2 centimeters. 2 centimeter at x is equal to 0. So that's what we're gonna do. So 2 centimeter, just keep it. Amplitude is 4 centimeter cos. So we check this displacement at x0. So this is 0 plus this wave is at 0 seconds. 0 seconds plus phi. So then your phi is, which is the initial phase, inverse cos 2 over 4, which is 60 degree. Okay, in radian you can convert to radians if you want. So then we're ready. So go back to this equation, then you can write down the complete wave equation now, right? So amplitude is 4 centimeter, for write down centimeter, cos k is 0.52 radians per meter, so x. And remember, this wave is traveling forward in positive x direction, so you need a negative sign here. Okay, not positive, negative. And omega is 13 t, plus phi is 60 degree. You can convert into radians if you want, but just keep it as a degree. So that's your complete wave equation. So this equation represents the given equation, because if you simulate this in computer, you know, using this as a function of x and t, you will get a traveling wave whose speed is 24 meters per second. Okay, next is what is the maximum transverse speed of the particle of the medium at t0. So again, particles, to find the transverse speed, right? Particles only execute, particles are executing, you know, just simple harmonic motion. So you can just use the simple harmonic motion formula. So what was the maximum velocity formula from simple harmonic motion? It was just a omega, the magnitude of the maximum velocity, right, in simple harmonic motion, if you remember from simple harmonic oscillation, just a times omega. So a is amplitude, which is 4 centimeters, 0.04. Omega is 13. All right, that's it. So 0. Meters per second. So that's your answer. So here's the next problem, simple couple of problems. So the sinusoidal wave with an amplitude 1.5 centimeter, frequency 100 hertz, travels in with 200 meters per second in positive x direction. Write down the equation for the wave. And here, since you're not given any initial conditions, so we just consider the initial phase. You can just, if it is not given more information, just consider the initial phase at 0. So again, what do you need? Let's see, again back to the same problem. A cos kx plus and minus omega t, right? And plus some initial phase which we consider 0. So plus is for negative direction, negative is for wave traveling in positive direction, right? So let's see, what do we need? So k is 2 pi over lambda. You need lambda from here, but lambda is not given. So lambda is speed of wave divided by frequency. So speed of wave is given as 200 meters per second. Is the wave pattern is traveling at 200 meters per second. Frequency is 100 hertz. So 2 meters, right? So then just put it here, 2 pi over lambda, and then 2 pi over lambda, right, is 3.14 meters. right? Per meter is the unit. And you're given frequency of omega is 2 pi f, so 2 pi times 100, so that's going to be, so calculate that. So 100 200 times pi, so 628 is unit is radians per. Okay, I guess that's all you need. So then your given wave equation is amplitude is 1.5 centimeter, that's given. Cos k is 3.14 x, its unit is radians, its unit is per meter, or radians per meter, right? Radians per meter is fine, it's radians per meter. Okay, and plus and minus, so it's traveling in positive x direction, so you need minus. Omega is 628 t plus 0 phases, because we consider 0. So that's your complete wave equation, right, for this particular wave. Okay, let's do one more. I'm gonna quickly solve one more simple problem. So here's the FM radio station broadcast at a frequency of 101.3 megahertz. What is its wavelength? And radio waves are electromagnetic waves, and all electromagnetic waves travel with the speed of light in vacuum, air or vacuum. Okay, so that's unlike a sound wave, which is mechanical wave. Electromagnetic waves have a constant speed in air or vacuum, which is 3 × 10⁸ meters per second. There's the speed limit. So that's pretty easy one. So speed of wave speed, as you know. So in this case c, right, because this is an electromagnetic wave, we represent speed, electromagnetic wave speed in vacuum as c, is lambda times frequency. So what's the wavelength? So c over frequency. So c is 3 × 10⁸, and the frequency of the given FM is, it says FM signal is 101.3 megahertz. Megahertz is 1 million hertz. So 113 × 10⁶. So lambda is then that's your lambda, right? So you can calculate that. 8 divided 6, so it's 2.96. So that's the particular radio wave wavelengths. Radio waves are very shorter frequency, low frequency waves. There's a much longer wavelength waves, radio waves. Here's the next problem. So it's asking what are the speed and tension in the string of a transverse wave in a rope of length half a meter and mass 60 gram, whose wave equation is given by this. So wave is traveling in a string, and its wave equation is given by this equation, and it says the total length of the string is half a meter and its total mass is 60 gram. So finding the wave speed is really easy, because you just need to compare now with the standard wave equation, traveling wave equation, comparing with our standard traveling equation. And remember, traveling wave equation is some amplitude cos function, and you have kx, and it has plus, it's traveling in the negative x direction, plus omega t, right? So just by comparing that, the wave k is called the wave number, right? From here it must be 2.0, and its unit is per meter. And what is omega? Omega must be 30, right? And its unit is radians per second, or per second. So then the speed of the wave is then just k omega over k, right? One of the formula for speed of wave is omega over k. That's it. So omega over k, and the speed of wave is 15 meters per second. So that's the first part, right? So second part of the wave now is asking what's the tension in the string. Okay. So to find the tension in the string, another formula. So the speed of wave on a string depends on the string properties, all right, and the tension, how much tension you put. And the formula is force of tension, right? Force of tension divided by the linear mass density, which is mass per. So what is mu? Mu is the linear mass density, which is just the mass per unit length. So mass is 60 grams, so 0.06, because it has to be in meter kilogram, and divided by half a meter. So mu is 0.12 kilograms per meter, right? And then just back here, then you can find the ft. So first you have to square it, and f of t divided by mu. So force of tension, so the tension in the string, is just mu v square. So mu is 0.12 times v, we have already calculated, 15 square. So that's going to give you force of tension as 27 newtons. So the tension in the string is 27 newtons. So here's the next question. So it says a transverse wave is traveling along a string in the negative x direction. The plot of the displacement as a function of position is given at t is equal to 0. That means you have a traveling wave, and you just take a snapshot at t is equal to 0 second, and this is the y versus x graph. Okay, this is not y versus t, this is y versus x, right? Because you just take a snapshot of the traveling wave at t is equal to 0 seconds, right? And the scale is given by, it's a 4, this y of s, this is 4, right here, this scale is 4 centimeter, right? So each is 1 centimeter, each box is 1 centimeter. Okay, so and the string tension is 3.6 newton, and its linear mass density mu is 25 grams per meter. What is the maximum transverse speed, right, of the particles in the string? So remember, wave equation is, the traveling wave equation is this, right? A cos kx minus omega t, and let's say there's no phase shift. So then the transverse speed, right, of the particles of the medium, here in this case particle of the string, is just the let's say the transverse speed, let's say u, right, is just a derivative of this function, right, with respect to time. And if you do that, so cos negative a omega, right, and so positive, because it's going to give you minus omega t, right? Yeah, so cos will give a negative, 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 positive. So sine function kx minus omega t, right? So this must be the maximum transverse speed, right? It's just from the simple harmonic oscillation, right? Because each particle in the given medium, it just works as a simple harmonic oscillator. So u max, which is the maximum transverse speed, is just omega a, right? So what do you need? So amplitude is given from here. So amplitude, you can find the amplitude from the given, because it's y versus x. Amplitude is the maximum displacement. So it's for 5 centimeter, right? 5 centimeter, that's given, convert into meters. So what else do you need? Now you're going to need frequency, because 2 pi frequency amplitude. You already know amplitude, but you don't know frequency of the wave A. So how do you find the frequency? So frequency is given by this, actually, because this is a y versus x curve, right? It's the actual wave. So peak to peak distance is the lambda. So lambda is the peak to peak distance, which is so 10 5 so this is 45 minus 45 centimeter, right, minus 5 centimeter from that scale is 40 centimeter is the wavelength, right? So what is the frequency then? So frequency is v speed divided by lambda, but speed is in terms of force of tension divided by mu, right, divided by lambda. So what is force of tension? Tension force is given to you. So 3.6 divided by, what is mu? Mu is the mass per unit. It says 25 gram per meter. So you must convert into kilograms. So 0.025, right? That's the speed divided by, what's the wavelength is 40 centimeters, is 0.4. So that's going to get you the frequency, right? So the frequency of the wave is 30 hertz. Now you just then put it back here. So your U max, which is the maximum transverse speed, that's what it is asking, is 2 pi. Now frequency is 30 hertz. Amplitude is 5 centimeters, so 0.05. So that's the U max. The maximum transverse speed of the particles of the string is 9.4 meters per second. Okay, so that should be the answer. Okay, so here a couple of things, right? So to find the maximum speed you need omega A, but you don't need the frequency. First you have to find the frequency like this and put it back here.